Kinetic energy penetrators forced armor to become a layered engineering system rather than just more steel.
Early armor philosophy relied heavily on thickness and slope to defeat solid shot. Armor is a contest between material strength and the physics of impact.
Anti-armor threats evolve in waves, and armor must chase the next wave without becoming too heavy to move.
Slope can increase effective path length, but it's not a universal answer to every penetrator type.
Modern KE rounds are designed for high velocity and efficient energy transfer, not explosive effects.
As we visualize mass times velocity, kinetic penetration is about concentrating enormous energy into a tiny area.
Early penetrators emphasized hard materials and blunt force, limited by the guns and metallurgy of the era.
Armor is always traded against mobility, too heavy, and the tank loses the ability to fight where it must.
Sub-caliber concepts allow a smaller penetrator to be launched efficiently from a larger gun.
Long, slender penetrators aim to stay stable and deliver energy in a narrow channel.
Fin stabilization became important as penetrators grew longer, and spin stabilization became less ideal for extreme length to diameter ratios.
Armor responded by becoming deeper, more complex, and shaped to disrupt or erode penetrators.
Material science, hardness, toughness, and high-temperature behavior became decisive on both sides. Many kinetic energy impacts behave like extreme speed material flow, not simple drilling.
Frontal arcs are reinforced because tanks are designed to fight nose-on whenever possible.
Weight limits force uneven protection, strongest at the front, weaker on flanks and roof.
Spacing can destabilize, yaw, or fragment a penetrator's path, forcing it to waste energy.
Composites can combine hardness and energy absorption in ways steel alone cannot.
Survivability includes controlling fragments, even when armor is stressed.
Modular armor allows for critical upgrades, ensuring that as penetrator technology improves over the decades, the defense can adapt.
Longer rods generally improve penetration potential, driving armor thickness and complexity upward.
As you can see, modern tank shapes often reflect exactly where designers concentrate the most effective protection. Flatter trajectories and extreme high velocity are critical for long-range engagements, proving the effectiveness of these KE darts.
Bigger guns can enable higher energy shots, but they also reshape turret size and weight distribution.
Every armor upgrade is a compromise among protection, mobility, cost, and transport limits.
As KE penetrators became longer, faster, and tougher, armor shifted toward multi-layer arrays and modular blocks. As you can see here, inducing yaw can reduce effective penetration by spreading forces off-axis.
Geometry can be as important as material, controlling stress waves and failure modes.
Reactive armor emerged to counter shaped charges primarily, while KE defense relied more on deep composites and spacing.
Observe how the frontal armor angles dynamically. This maximizes the armor's effectiveness, illustrating that facing the threat correctly is paramount to survival.
Field upgradable armor reflects a world where penetrator improvements can arrive faster than new tank generations.
Survivability design increasingly focuses on what happens after armor is stressed.
Compartmentalization can reduce catastrophic loss by channeling energy away from crew spaces.
Even partial penetrations can be deadly without internal mitigation. Real battlefields are cluttered. Armor must work across angles, not only perfect test shots.
Modern threats from above increased attention to roof protection, though weight constraints remain severe.
Add-on protection often aims to change fusing or standoff for some threats, while KE defense still depends on core armor depth.
Tiny grain structures and specific heat treatment choices can significantly influence how armor absorbs shock.
The armor design is as much about managing shock waves as stopping a rod. Designers concentrate on the golden zone, the area most likely to be hit in head-on engagements. Protection is uneven by necessity, so doctrine emphasizes posture, cover, and reducing exposure.
Armor is only one layer of survival. Terrain and tactics are the other layers.
Every extra ton can reduce speed, range, bridge access, and strategic transport options.
Heavier armor demands stronger suspensions and engines, reshaping the entire vehicle ecosystem.
Infrastructure limits can be as decisive as enemy weapons in how much armor you can carry.
Modern armor aims to break the penetrator's efficiency by forcing it to spend energy across multiple interfaces.
Composites can disrupt penetrators via differing densities and fracture behaviors, complicating the impact physics. Protection must function across extremes: hot deserts, freezing winters, and constant vibration.
Kinetic energy improvements and armor upgrades form a long feedback loop, creating a continuous escalation with no permanent winner.
Weak points, joints, seams, and openings are where designers fight hardest to minimize vulnerability.
Crew visibility features must coexist with protection, creating constant design tension.
KE penetrators push tanks toward deep, modular, composite-heavy armor layouts, while internal survivability features grew.
Modular armor means protection can be refreshed as threat intelligence changes.
Evaluation is rigorous because tiny changes in angle and speed can produce very different results.
Modern armor design is guided by data, high-speed imaging, sensors, and post-test forensics.
Computational modeling helps explore thousands of design variations before expensive physical trials.
Armor design increasingly includes architecture, where people and hazardous items are placed.
Relocating vulnerable items and adding venting concepts can improve crew survivability even under extreme damage.
As this demonstration shows, urban angles challenge traditional frontal arc assumptions, significantly increasing the value of side and roof improvement.
As threats diversify, tanks receive additional layers, each adding protection but also weight and width.
Increased armor bulk can reduce maneuver space, another hidden cost of protection.
The modern battlefield demands multi-threat armor, yet solutions effective against kinetic energy may be less optimal for emerging threats.
Designers attempt to harden traditionally weaker zones, but geometry and weight limits make it difficult.
Exposure and silhouette matter. Sometimes the best armor is not being hit at all.
Tanks remain complex machines whose protection must also manage heat, maintenance access, and reliability.
Strategic mobility is a hard limiter. Armor cannot grow forever if it can't be moved where needed.
KE penetrators sharpen this triangle by demanding heavier frontal modules and better internal survivability.
Armor design is shaped by expected opponents, engagement distances, and battlefield geography.
The front arc remains the main shield against KE threats, often incorporating the thickest, most complex arrays.
Incremental improvements attempt to reduce vulnerability to side hits without ballooning weight too far. Modern armor must address top angles as battlefield sensors and munitions evolve.
Shock management and ergonomics matter, because survival also means staying functional, even after near misses.
Tactical discipline is crucial. Angling the hull, constant repositioning, and minimizing exposure ensure that the armor engineering works as designed.
Next-generation armor trends emphasize quick upgrades,
weight-efficient materials, and integrated active protection concepts.
Modern survivability becomes system of systems, where detection and interception may complement passive armor.
The story of KE penetrators is also the story of engineering under constraints. Physics never negotiates.
The contest continues. Penetrators seek efficiency, armor seeks disruption, and both sides refine materials and geometry.
Modern tank armor design is the visible result of decades of KE pressure. Layered, modular, and built around crew survival.
Arthur concludes that kinetic energy penetrators transformed armor from simple thickness into smart structure. Deep composites,